I'll direct you to the, I'll direct you to the first inside page. These are all the words we're going to encounter. The word term, coefficient, variable, exponent, etc., etc. I think most of these we'll get to today. We might not get to all of them, but this is just the vocabulary for this unit. So you should be familiar with all of these words, at least probably by the end of this week for sure. So we're doing an intro. We're going to learn the vocabulary, identify different types, and the parts of polynomials. So again, I think I just talked about this. So I'm just going to jump to this. Some examples of polynomials are 2x, x squared plus 7y minus 14, 81m squared minus 2.2y to the power 4, 3/4 p cubed plus q squared, right? We've seen all of these symbols now, right? We did a quick review of exponents and how to say those words. And now what we've done is we've introduced variables. Any letter of the alphabet can be used, quite honestly. Sometimes in science, they tend to use variables that reflect what you're studying more. So the R makes perfect sense that R stands for radius and A stands for area. When we're using formulas like that, they're pretty descriptive. But just in a generic math sense, if we're just giving you polynomials to work with that don't have any meaning beyond that they're just a polynomial expression, any letter of the alphabet can be used, of the English alphabet, right? Any letter of the English alphabet represents what we call the variable. That means I can substitute any number I want in for that variable. What does 2x mean? What are the 2 and x, how are they joined together? Does anyone know? Multiplication, right? Multiplication is that one math operator that doesn't need a symbol. So when you see a 2x, we typically pronounce it 2x. It really means 2 multiplied by x. I don't know what x is. I haven't told you what I want x to be in this particular case. So we just say it's 2x. This would be x squared plus 7y minus 14, etc., etc. I said any letter of the alphabet can be used. Quite often you see lots of x's and y's in math statements. Anyone know why x's and y's are used? No? Well, one of the reasons is that algebra, the 2 main branches of math are the algebra, so actually doing the pen and paper stuff with numbers, solving problems algebraically, so just using formulas, and then also graphing, right? We can solve a lot of math and science problems graphing, and we use this coordinate system when we're graphing, the XY coordinate system. Anyone ever used this before? Yes. Yeah, so the horizontal axis is the x-axis and the vertical is the y. So that's one of the reasons, and we'll be moving slowly towards using graphing in our, the unit that we talk about linear relations, we'll be doing graphing. So that's why you see a lot of x's and y's, but really any letter of the alphabet can be used. Some letters are used more than others because some letters don't really lend themselves. For example, the letter O, you can see why O wouldn't be used as a variable, right? Because it looks like 0, right? L looks like 1, so there's certain ones that just aren't really that nice to use. X and Y, again, are common because they relate to graphing. So let's do the parts of a polynomial so you can use the words properly. So when we're just looking at 2x, this means 2 times x. 2 is called, when it's attached to a variable, 2 is called the coefficient and the x is the variable. So the letters of the alphabet are called the variables. 3x squared, so I've added an exponent. Of course, the exponent is the 2. We saw that in the previous unit. The x is the variable, the 3 is the coefficient. Okay. This one at the end you might not see it here, but the term minus 5, that is a polynomial. It's a really simple polynomial. It has no variable attached to it, so it's not really a coefficient. It's just called a constant then. So anytime you just have just a number, constant. So if I look up here, are any of these 4 polynomials, do any of them just have a constant? I see lots of coefficients. Is there any constant here?
14.
The 14, right? The negative 14 would be the constant. Okay, so let's flip. Now, this is probably one of the more challenging things to think about today because it's really going to be a nice, I think, a nice easy class or two to get into this. They're really not, once you understand the family of polynomials, it becomes, they become pretty easy to work with. So the only thing you have to remember is a polynomial can only have whole number positive exponents. Okay? The following math expressions are not polynomials. Okay, so let's just discuss it. We won't be studying not polynomials. We're just studying polynomials. But just so you know, just at the very beginning, why they're not polynomials. They do represent some kind of a math function, but they're just not polynomials. So it says whole number positive exponents. What's the problem here in the 6x plus 10x to the negative 4? Remember, they can have only whole number, so no fractions, positive exponents. What about this guy? What's the problem here? Yeah, the negative 4. Negative exponent means not a polynomial. Okay, so I'm just going to record that just so you have that written down somewhere, or you can remember that. So a negative exponent, not a polynomial. Now, some of this is a little obscure because I know we're just refreshing our math skills, so it might be a little rusty. Anyone want to know why the root of 7m is not a polynomial? This is a tricky one. Okay, that's a square root sign too, so that's not a division sign.
Oh, sorry.
That's okay. But this is something that you might not know. You maybe have never learned it. But the square root symbol also represents exponent 1/2. Okay? So the square root of 7m is also, I can replace the square root symbol with exponent 1/2. So therefore it's not a whole number exponent, right? Now, did anyone ever come across that in any of their math? Okay, you might not have. I just want to show you something. So this is kind of, it's not that obscure. It actually comes up quite a bit. So something to file away. Everyone could figure this out with their calculator, right? We did cover this in Unit 1, right? Unit 2, the square root of 16. Everyone knows what the square root of 16 is, right? Yeah? What's the square root of 16? 4. Now, this is the same way of writing it. This is sort of slightly more pre-cal-ish, but 16 to the power of half is 4. They're just two ways of writing the same thing. I'm going to show you on my calculator that I'm not making that up. But just remember, when you see the square root symbol, it also represents the exponent 1/2. They are the same thing. So on my calculator here, I've got the square root of 16. That equals 4. We knew that. If I go 16 to the power, and I'll just use brackets so you can see what I'm typing in here, to the power of 1/2, right? That's 4. Okay, so they mean the same thing. So when you see a square root symbol, that's representing a fractional exponent, not a polynomial. And these two kind of are the same thing. This is another thing that you will review, do a little bit of reviewing on. Anytime we have a variable in the denominator with an exponent, it also can be written as an exponent in the denominator can be moved upstairs to become its opposite. So that's negative exponent, not a polynomial. Same as this guy, right? This guy, 5x plus 2y. Okay, if I want to move the 9p up to the top, or I could leave the 9 down here, The p has exponent 1. I can move him up top and he becomes a negative 1. Okay? I guess the takeaway is no variables. This is what we'll record. Variables can't be under a radical sign, because that means they're really attached to a fraction exponent, and can't be in the denominator. I think that would suffice, right? Here the x squared, the variable was in the denominator, not a polynomial. Negative exponent, not a polynomial. Square root, radical, not a polynomial. And a variable was in the denominator. So if you just keep that in mind, they can't be under a root sign and they can't be in the denominator, right? Then you know, if they're just sitting at the top level with no negative exponents, they're going to be a polynomial. Now, you're not going to be heavily tested on is this a polynomial or not. I think there's a couple questions in the first assignment, but our course is just to study polynomials, so the ones that we're going to be doing math with are going to be polynomials, okay? So let's just see if we can figure this out. For each of the following terms, list any coefficients, variables, and or exponents. So let's do the first line, 2 lines together maybe, and then I'll give you some time to complete the chart, and then we can check in with each other. So negative 3x to the power 5. Is there a coefficient in this term?
No. Whole number?
Yeah, the coefficient is attached to variable, right? So is there a variable, x? Is there a number multiplied by the variable? Yeah. So the coefficient is negative 3. The variable would be x. The exponent would be 5. Okay? Is there a coefficient?
No.
No. What did we call the 5.2? Yeah. I'll write this down. No coefficient. 5.2 is the constant. No variable, no exponent, none visible, right? Okay, I will do the next one with you. I wasn't going to, but I will do it with you. Is there or are there variables? Let's do the variables first. Are there any letters in this term? Any alphabet letters?
Yes.
M and N, right? Are there any exponents? 2. Okay. Is there a coefficient?
Yeah.
Okay. Be very careful. The coefficient is actually a fraction 4/7. Okay? So, if I look closely, this is still a polynomial because there's no variable in the denominator, right? But this can be written as, would you agree, that if I wrote this as 4/7 m squared n, and you can think of the 4/7 being multiplied by the m squared n, that represents the same thing, doesn't it? Yeah? Okay. Your eyes don't see that? I'm just actually honestly asking you. Okay, let's look down here. Okay. It's hard to see at the beginning, right? Till your eyes adjust to the new. So let's say I had 4/7 and I multiplied it by m squared n over 1. Okay? Yeah? Okay, what do I get on the bottom when I multiply fractions? 7 times 1 is 7. Kind of getting a little ahead of myself, I guess, here, but 4 times this, I can't really, they're not the same, right? So the best I can do is just record it as 4m squared n. Do you see it now? Yeah. Another thing that many students can't seem to see very easily until you become accustomed to it is a lot of times you might end up in polynomials with x over 2.
Excuse the interruption. If you're missing a cell phone from the charging box, please come to the office. Thank you.
That's a polynomial, right? It has a variable, there's no variable in the denominator. We can have a number in the denominator, no negative exponent. So that's a polynomial, x over 2, x divided by 2. I could write this as 1/2 x. Doesn't that represent the same quantity? X divided by 2, or half of x, right? That represents the same quantity, half of x, x over 2. Now, sometimes there's an advantage by having the coefficient kind of written as a fraction. Sometimes it's just neater to write it like this, but these are equal. Maybe record this somewhere on your sheet. Just remember this. Note that these are the same. Because sometimes different textbooks record their variables and fractional coefficients like this. Some textbooks like to have it really all in the open for students. It's just kind of almost a preference thing, but they mean the same thing. Okay, so be careful about that, because there's one coming down, there's a couple coming down here, right? So I'll give you a minute or two just to fill in the rest of the cells, okay? This is just for practice. And everyone has the book, correct? Yeah? Okay. Okay, how'd we do? Variables are x and y, agreed? Exponent was 5 on the x and 3 on the y, right? What's the coefficient? 1. So there's an invisible 1, right? If there are variables present but no number visible, it's a 1, an invisible 1.
What'd you say?
Yeah, it's a 1. If there are variables, and there are, right, Cliff? Mm-hmm. But there's no coefficient present, there's always assumed to be a 1 there. It's an invisible.
So
Okay?
would that be 2 coefficients?
No, just 1. Each term has a coefficient. This is regarded as one term. So I know it's rough at the beginning, not mathematically, but just accepting everything I'm telling you. A lot of this stuff is just by convention, right? What's evolved over the years, what's accepted practice. So accepted practice is If there's a coefficient of 1, it's not written because it's not necessary. And typically math and science people try and be concise because that's really what we're doing, right? We're converting English language and problems in our language into a math language. Math language takes this much space. English language would take this much space, right? So we try to be as concise as possible. Okay, the coefficient of the next one, negative 3m to the power 4 over 5. Negative 3/5 is the coefficient, agreed? Okay, the variable is 5, the exponent is 4. Coefficient 2k, coefficient is 2, the variable is k, and I guess every variable would technically have an exponent too. The exponent on the variable would be an invisible 1. And if you just said no exponent, that's fine too, but every variable also has an exponent, understood? So if there is no exponent present, it's a 1. Okay. And again, you're just accepting kind of math facts and what's conventional, so this beginning stuff is just, a lot of it's just, okay, well that's what they're going to call the number attached to the variable is the coefficient. You just got to go with that, right? Coefficient would be negative 7/3. Variables are a and b. The exponent is 5 on the a and 3 on the b. Okay, so that's, we good so far? Relatively speaking?
You want to store that on the A?
No. That's just for me conveying to you. So all of these were all polynomial terms, but they were really small, right? They all just consisted of one term. Can you see that? Just one little piece. They can be really complicated, as in they can have a fractional coefficient. This is quite a complicated one, right? Negative 7/3, really what this reads as, negative 7/3 times a to the power 5 times b to the power 3. They can have more than one variable, exponents, they can have a fractional coefficient, but this is just regarded as one piece, one term. Multiplication and division, just glue a term together really tight, but it's still regarded as one term. The only thing that separates terms from one another are adding and subtracting, plus and minus signs. So now we go to naming. Polynomials have different names according to how big they are. Okay, so the three names that we kind of use commonly, but we stop at, we use the term monomial, binomial, and trinomial. So this has been a term with 4 pieces to it. Would be called a quadrinomial, but we don't use that. We just use these 3. Anything larger than 3, like 4 and up, we just refer to as polynomial, just a general polynomial. And by the way, the word polynomial just means the whole family of polynomials. Poly means many, and nomial means terms, many terms. So all of these actually are polynomials. They're just in the family. It's just that these 3 guys have specific names as well. So a monomial has 1 term, binomial has 2. Can you see how it's separated by the plus sign? 3 terms. This one has 4 terms. Can you see 1 term, 2 terms, 3 terms, 4 terms? Okay, maybe I'll do that. These are your 3 terms. These are your 2 terms. This is your 1 term. Polynomials can consist of thousands of terms, I guess. The ones we use in math class typically I don't know, the most you'll see is maybe 10 terms, but as we move through applied math, they won't be crazy. Like probably the biggest you'll deal with on a day-to-day basis would be 4 terms, okay? Again, this is just 4 terms, 1, 2, 3, 4. But anything bigger than a trinomial, we're just going to refer to as a polynomial. Again, don't forget this. Just when the coefficient 1, it's not explicitly written. Okay, so let's take a look here. Now you're just getting your eyes accustomed today to looking at polynomials because you haven't seen them yet in this class. And then I guess just kind of trying to connect all the parts with what your eyes see. So, refer to the polynomials below to answer the questions that follow. All right, so they're identified as A, B, C, D, E, F. Which polynomials are monomials? Any others? A and E, right? Okay. It's a constant, but it's still a polynomial. Okay, what about trinomials?
C.
C and F, I agree. C and F, right? Does anyone recognize F? F is a formula. No? This is the surface area of a rectangle formula. Which polynomials have a constant term? Well, E for sure. Any others? I think C does, right, Danielle? It's got the 8. Any others?
E.
C, D, and E, right? The 8, the 1, and the minus 20. Which polynomials have a coefficient of 2?
A.
And F, right? Okay, so again, just reinforcing vocabulary. All right, let's keep going. Stop me anytime you have questions. Okay, we've got a polynomial, 10t squared minus 3. How many terms do you see? 2. 2 terms? Does this one have a special name? Does a 2-term polynomial have a special name? It's a binomial, right? That word bi from like bicycle. What is the coefficient? 10. How many variables are there? 1 variable. And what's the name of the variable? T. You see a lot of T's in math and science as well. Why would we use the variable T in math and science classrooms? What do you think T would stand for? R, yeah, R stands for radius, A for area, T stands for time. So anytime you're doing an experiment involving time or you're studying something involving time, T is a quite common variable. What is the constant term? -3, okay? All right. 2 more little examples to do, and then I'm going to give you some time to work on assignment 1. I am going to stop here for 1 sec because I have to inform you guys I'm not here tomorrow because I'm at a PD all day. There is a math teacher in tomorrow. But I'm going to throw something out at you guys. I'd like to get to assignment or example 2 tomorrow. Instead of giving you work time, how do you feel if I give you work time tomorrow in class and I teach you lesson 2 as well, or start lesson 2? How do you guys feel if I push through rather than leave it to a sub? Is that okay for people? Because I think it's easier to, when you're used to how a person explains it, it's probably easier for me to do it. So, okay, so are you guys okay if I actually even leave this for you guys to do? Example 2 and 3 and 4? Okay, so let's just fast track over here, and of course I'll catch you guys up Thursday. I don't want to be away, but I have to be away tomorrow for. So let's jump to combining. So lesson 1 is just about vocabulary. I'll let the sub help you out with that. I'm sure he's fine with that. But the big deal comes now. We're going to be doing some math. So combining polynomials means combining polynomials. We already combined numbers, we combined fractions. It just means adding together the parts you can add together. Now the thing that's a little different about polynomials, which is kind of interesting, when you had a big string of numbers in arithmetic, you basically kept working till you added all the numbers together and you got a nice little one value for the answer. It doesn't work that way in polynomials. Polynomials are a little fussier. And the reason is they have to be combined using like terms, okay? That means only certain polynomials can be added to the others. So let's again review some of this beginning stuff. Again, by convention, polynomials are written in a certain way. So polynomials are usually written in descending order, and we say descending by looking at the exponents, okay? So when you have the same variable being used, and sometimes you don't, but I'll just discuss that in a minute. This polynomial, this is a trinomial. This is a trinomial. It's the same trinomial. It might look the same because it wasn't written in proper order. First, it was given to you as 6m plus 2 minus 7m squared. The proper order is minus 7m squared, or negative 7m squared, plus 6m plus 2. Notice how the m with the largest exponent was written first, then the m with exponent 1, and then the constant. The constants are always written last.
Would it give you different answers?
No, because we haven't, all we're doing is arranging, Blanca. It's the same three pieces written, the same three pieces are written, they're just written in a different order. So the order, it doesn't change the value of the expression at all. Okay, and there's a reason we're doing this, but I'll get to that in a moment. But it says write the following polynomials in correct order. Identify any polynomials that are equivalent. So again, just kind of train your eyes to see this new language. So for this one, and I'm going to kind of jump through a couple of them just to make sure I get through all the important stuff today. This one's not written in proper order, is it?
No.
Who should be written first? Yeah, 7x squared, and then the positive 2x, then the minus 4. Remember, if there's not a symbol written in front of the lead term, it's a positive number, right? Let's jump to a larger one. Let's jump to E. Which one should be written first? 6m cubed, right? And then a positive m squared, then a positive 6m, and then the negative 9. Okay? So there, one of the things was write them all in the same order. Are any of them identical? Let me jump to H. If I wrote this in the proper order, whoops, that's a cubed.
Yeah, that's what.
Thank you. This would be negative 6m cubed, positive m squared, positive 6m, positive 9. Are they identical? No, they're not, right? The signs of these last two terms, so they weren't identical. Let's try this one. Let's try D. 7x squared would be written first, then a positive 2x, then a negative 4. So these two are identical, right? I would say that A and D are identical. Are identical polynomials. So that's what that lesson was about. I'll complete this example in my notes, and I'll post the examples on the blog. Okay, so you have all the examples, but that's all they wanted us to do here. Just like if I do this one really quick, this was a 7x squared, then a minus 2x, then a positive 4. That's not the same, right? So A and D, so far I've identified A and D are identical. There might be more identicals, but that was just recording in the proper order, okay?
This what you call like collecting like terms?
We're just getting to that, yeah. This is not collecting like terms. This is just writing in proper order, okay? I'll say one more thing here. I thought it was written. The other thing about polynomials, I think it's coming up, but I'm going to identify it. Also, when variables occur, in the same term, the variables are written in alphabetic order. Alphabetic order. That's another convention. So, if I had a term like, how about this? 14 NMP. Okay? That's not correct. That's not convention. Should be written as Okay, you kind of have to go through your alphabet some days, but it's 14 M N P. Okay? So you follow the order of the alphabet. So when you're actually listing, you know how like the fractions, we were kind of fussy, we said put them in lowest terms. With polynomials, make sure that you're written in descending exponential order, and also write your variables in alphabetical order. Okay, so let's see what I can get to. And then tomorrow will just be a big work class, right? And I think I'll just stop after this page because I don't want to overload you too much, but and then I will kind of cherry pick which questions I want you to do. Okay. All right. Like terms. As I said, when we had a big arithmetic statement, we just kept adding all the numbers together to what we got at one value. That's not always the case with polynomials, because polynomials can only be combined if they are like terms. So like terms are terms that only differ by their coefficients. What does that mean? That means they share exactly the same variables with the same exponents. So to simplify polynomial expressions, we can only combine like terms. What we do is we combine the coefficients like normal, like we did in arithmetic, and then the variables stay the same. So notice that when like terms are combined, the exponents and the variables remain unchanged. It's only the coefficients that change. So this is why we're really fussy about making sure your variables are written in alphabetical order so that you can easily identify the like terms. So identify the like terms of each group. Okay, let's see. I have a 7a squared, a 4ab, a minus b, a 7c, and a 5b. Are there any like terms in this group?
B and 5B.
There's no a squareds other than this guy, right? There's no ab's together. There's no c's. So the only like terms are the negative b and the 5b. I have a coefficient of -1, coefficient of 5, but they're alike, right? Because they share the same variable. Okay, what about this? Are there any other x? I have a 4x squareds. Are there any other x squareds? Just x squareds? Yeah, there's this one, and this one, right? There's no other xy. There's no other just pure y. So done. Okay, what about this one? Are there any other mn's? Yeah, it's written improperly, right, to throw you off, but it should really have been written 10 mn. So I have a 16 mn and a 10 mn. And these guys don't have any other partners. M and m squared are not like terms, and n is not a like term with anything. Like the m and the m squared, they both have the variable m in it, but because this has exponent 2 and this has exponent 1, they are not regarded as like terms and can't be combined. Okay? Now, why you want to identify like terms, and this is the last thing I'll say today, and then I'll stop talking and give you guys some time to think and ask questions and stuff. Simplify each of the following by combining like terms. So we're actually doing some math with polynomials now. Combining like terms means adding or subtracting terms in order to simplify. So we're really worried about simplifying and doing whatever math we can. A 4x and a 3x, because they're like terms, can be combined. What does your gut instinct tell you that the answer is? 7x. If that's what your gut told you, you've got good instincts. Okay. Once you identify the like terms, the variable will stay the same, and you're just concentrating on the coefficients, right? A 4 and a 3, that becomes 7. Okay, here, they're all like terms, so my final answer will be something m. So I have a -6, a +11, a -3. We spent a bit of time combining numbers way back. It's going to be a positive number, and it should be a +2m, right? because you have -9, positive 11, resulting in a 2, right? Okay, so these are all x, y's. They
Do you mind breaking that one?
no,
I thought
yeah.
it was 6 and 11.
Did you do it piece by piece, Blanc, or
I
did you?
6 and 11, so that would
Okay,
be
so that gives you a positive 5,
and then,
positive 5m and a -3m.
okay, yeah. I see what
Yeah,
it is written
that's
down
good,
on.
yeah. Okay, so this one, they're all like terms, so that's great, they can be combined. A positive 15, positive 2 is 17 minus 10, leaves us with a 7xy, okay? So in some ways, the math becomes easier in a way, the arithmetic, because we're also throwing at you the variables, so it's not going to be as hard mathematically as combining fractions or anything like that, because now what we're doing is we're getting you to sort through the variables and kind of collecting those and then doing the arithmetic. Let's take a look at this last one. 7 minus p squared plus 2p minus 1 plus 4p squared minus 9p. Okay, there's a lot going on. It doesn't really matter where you start. It matters how you display your final answer. But do you see any like terms? What are some like terms you see? Okay. So you're concentrating on the p squareds, which is kind of nice. Why did you go right to the p squareds, Unesa? That's the greatest. In the end, you'd have to write those guys first, so you just chose to do those first. That's fine. So I have a -1 and a positive 4. That results in positive 3 p squared, right? Okay, so those two guys are done.
2p and then 9p.
Yeah, and then I have a positive 2 and -9. What does that net?
-7.
-7p. So those two guys are done. Sometimes when I have a huge polynomial, I just kind of keep track of what I've worked through, like that. And then I have 7 minus 1. Positive 6. Okay, so if you, whatever you do, even if you if you did the 7 minus 1 first, in the end, you'd have to write it in this form to be written proper order. So 3p squared minus 7p plus 6. So that's what combining like terms of a polynomial is. Okay?
They're not actually asking for the answer, right?
That is the answer.
That's the answer.
Now, that's what you have to get used to. Polynomial answers are not going to look like arithmetic answers, right? Because I can't go any further. Would you agree with me? If you accept the fact that I can't combine these two guys because they're not like terms, I can't go any further, can I, Cliff?
No.
Now, the only way you can go further is if I said to you, okay, give me an answer if I tell you that p equals to 5. Right? Then you could substitute that value of p in here.
5 there.
Right.
Squared.
Yeah, but I'd have to tell you what p is. I'm not telling you that. So what you have to accept is the fact that your polynomial answers are not going to be these nice, neat little packages like you did in arithmetic, like equals 5, equals 2, equals... They're going to be... They themselves will be a polynomial. Okay? So I will talk about brackets on Thursday, and what I'll do is I think there are no brackets here anyway, so I'll get you to do assignment 1 and then see if you can make your way through 1 and 2 of assignment 2. Yeah. Now I also want to talk to people, so do assignment 1 and page 10 assignment 2. Assignment 1 and assignment 2. Of course, if you want to work further ahead, by all means, but I won't expect you to do tons more than that. I am gone tomorrow, but I am here on